Hello, what's on the menu for today? Monotonic divergent series of powers of 2. 1 plus 2 plus 4 plus 8 plus 16 plus 32, etc. equal to -1. We're going to go through 7 proofs. The first one, we're going to look at, as usual, the generating function. Proof number 2, we're going to do a direct calculation. Third proof, another direct calculation. Fourth proof, we're going to look at the intercept function. Fifth proof, we're going to look at the partial sum integral, the PSI. Proof number 6, we're going to look at Ramanujan summation. And the last proof, we will look at Abel-Plana summation. Proof number 1, generating function. So let GF for generating function be the ordinary generating function for the monotonic divergent series of powers of 2. Here it is, GF of x equal 1 over 1 minus 2x. That is the expanded form. And then if we evaluate the above generating function with x equal 1, we get GF of x equal 1 plus 2x plus 4x squared, etc. The expanded form, we replace x equal 1. It disappears here. We are left with the monotonic divergent series of powers of 2, started from 1, plus 2, plus 4, plus 8, etc. And on the right-hand side, it's 1 over 1 minus 2x, replace x with 1, 1 over 1 minus 2, 1 over minus 1, which is minus 1. So if we apply the fundamental theorem of divergent series of integers, we conclude that the monotonic divergent series of powers of 2 is stable, because the value of the generating function at the value of x generating the monotonic divergent series is equal to a finite value, therefore it's stable, and the sum of the stable monotonic divergent series of powers of 2 is equal to the value of this ordinary generating function after a projection of cube, but we already dealing with a rational here, at the value generating the series. In other words, x equal 1 give us -1. Proof number 2, direct calculation. Let's write down this series, monotonic divergent series of powers of 2, 1 plus 2 plus 4 plus 8, etc. equal S, S being the sum of the series that we try to determine. Let's write down the same series again, but shifted by 1 to the right. Right shift, single right shift. And we write it equal to S. So when we do that, we actually assume that the series is stable. In other words, the sum of the divergent series does not change when we insert a leading zero in front. In other words, when we right shift the series to the right. So let's do the difference. What do we get? 1 minus 0 equal 1, 2 minus 1 equal 1, 4 minus 2 equal 2, 8 minus 4 equal 8, etc. 16 minus 8 equal 8, etc. And on the right hand side, S minus S equal 0. So here we almost there, almost the divergent series of powers of 2. Just the first term is incorrect. We would like a 0 and we have a 1. So let's subtract the finite series 1. So we can see here it's a finite series because all the terms are zeros except a finite number of terms, in that case only the first term, and the value of that finite series 1 is equal to 1, the sum of the terms that are not equal to 0. So 1 plus an infinity of 0 equal to 1, that's trivial, and we do the minus. So 1 minus 1 will give us a 0, and everything else will remain the same. And what do we have here? We have seen it here. We have assumed the stability, S equal S here. We have therefore equal to the sum of the series, 0 minus 1 equal -1, and that value equal to S give us the sum of the original series. Once again, we have assumed the stability of the series. So that's good. In terms of generating function, we have the following: 1 over 1 minus 2x minus x over 1 minus 2x minus 1 is equal to, let's do some algebra, 1 minus x minus 1 plus 2x at the numerator over 1 minus 2x. The 1 simplified, 2x minus x become x. So we are left with x over 1 minus 2x. So that's just basic algebra. How do we interpret this in terms of generating function? So this one is equal, we just seen it as a monotonic divergent series of powers of 2. This one minus this one, which is a single shifted monotonic divergent series of powers of 2. Remember, the x at the numerator correspond to the 0 here, to the right shift with a 1 leading 0 in front. That's the x here. Minus 1, which is, like we just said, the finite series of 1. This one, which is equal to 1. So when you see that number 1 here, we interpret it as 1 times x to the 0 power plus 0x plus 0x squared plus 0x cubed plus 0x to the 4th, etc. Then we do the algebra, and we get x over 1 minus 2x, which gets interpreted as single shifted, again the x on top at the numerator, monotonic divergent series of powers of 2. Again, those represent the single shift. So that's how, in terms of generating function, we interpret the sum of series that we have done here, sum or difference of series that we have done here. All right. Proof number 3, another direct calculation. So 1 plus 2 plus 4 plus 8 plus 16, 32, etc. is equal to S. So finite series 1, we've seen it, 1 plus an infinity of 0 is equal to 1. Let's do the difference. 1 minus 1 equals 0, and the rest is identical. S minus 1 equal, of course, S minus 1. So here 1 minus 1 equals 0, 2 minus 0 equals 2, or the rest pretty much straightforward. I go fast. S minus 1 equal S minus 1, right? So now what do we do here? We multiply by 1/2. So obviously 0 won't change, but the rest will become 1 plus 2 plus 4 plus 8 plus 16. And that we have seen, it's equal to S minus 1 multiplied by 1/2, S minus 1 over 2. Now if we use the property of this divergent series, geometric series of 2, divergent series of 2, or monotonic divergent series of powers of 2, we know that it is stable, so S is equal to S minus 1 over 2. Solve for S, 2S equal S minus 1, S equal -1. That's it. So in terms of generating function, if we interpret what we just did, so 1 over 1 minus 2x minus 1, 1/2 multiplied by 1/2 the difference of those two divergent series. Oh, this one is divergent, that one is convergent, is equal to 1/2 1 minus 1 plus 2x. Of course, those simplify. 2x, the 2 will simplify as well. We are left with x over 1 minus 2x. In terms of divergent series, this one is a monotonic divergent series of powers of 2. That one minus the finite series 1 plus an infinity of 0, is equal to the single shifted, that's the single shifted term, monotonic divergent series of powers of 2. So this algebra, interpreted in terms of generating function, represent the calculation that we have done here. This one minus that one multiplied by 1/2. Divergent series minus that finite series, which of course is convergent, multiplied by 1/2 equal the single shifted monotonic divergent series of powers of 2. So another proof, but remember that proof use the property that the series, monotonic divergent series of powers of 2, is stable. Proof number 4, intercept function. So let's go step by step like the other videos. Step number 1, calculate the partial sum. So here is our divergent series, monotonic. 1, the first term in a sequence of partial sum is equal to the first term of the series always. 1 plus 2 equals 3, plus 4 equals 7, plus 8 equals 15, plus 16 equals 31, etc. So that is a sequence of powers of 2 minus 1. You can see 1 is actually 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, 32, 64, etc. Starting from 1, from the index n equal 1. So we express the partial sum S of n, uppercase n, which is the index that I'm using to number the sequence of partial sum. Let's express it that as a closed form expression. So the sum of n from lowercase n equal 1 to uppercase n of 2 to the n minus 1 is equal to, let's open the toolbox, is equal to 2 to the power of n, one more than what we have inside there, minus 1. Here it is, n being an integer. Step 3a, calculate the intercept point h of n as a half sum of two consecutive partial sum. So h of n is equal to Sn minus 1 plus Sn over 2, which in that case is 2 to the n minus 1 plus 2 to the n minus 1 over 2, which simplifies as 3 times n to the n minus 2 minus 1. Minus 1 over 2 gives us a minus 1. We have assumed, just to do that calculation, that the first term here on the left, which is not written, is 0. Implicitly, I am assumed to be 0. Step 3b, express the continuous intercept function h of x by replacing n, the discrete index, with the continuous variable x. So in that case, we just replace x n by x. Here it is. X is a real variable. Running out of space, let's move to the next board. Here it is. Step 4, evaluate h of x where x equals 0. So h at 0 is equal to 3/4 minus 1, which is negative 1/4. Therefore, the sum from n equal 1 to infinity of 2 to the power of n minus 1, which is again the monotonic divergent series of powers of 2, is equal to the h of 0 after projection onto Q, which is not necessary here because it's already a rational number. Here it comes here. Is this correct? Not the correct answer. So what did we do? Where did we go wrong? What did we do wrong? So actually, in that case, due to the geometric growth of this divergent series, we have to evaluate h of x where x goes towards minus infinity, or the asymptotic value. So h at minus infinity, which is of course a limit when x tends toward negative infinity of that expression h of x, which is 3 times 2 to the x minus 2 minus 1. So here it is. We can, when x goes to negative infinity, x minus 2 also goes to negative infinity. So we can simplify the exponent there. We can move the 3 in front and then the minus 1 outside the limit. So it's equal to negative 1 plus 3 times that limit when x goes to negative infinity of 2 to the power of x. This one, we know it will converge towards 0. Therefore, 3 times will also go towards 0, and we are left with negative 1. So the rational sum of the monotonic divergent series of powers of 2 correspond to the intersection of the asymptotic horizontal line y equal negative 1, that value that we found here, with the vertical axis. And that is the value of the h at negative infinity, which is the asymptotic value, limit when x goes towards negative infinity of that expression, h of x, projected onto Q, not necessary here because we already have a rational number, is equal to negative 1, and that is the correct value. All right. Proof number 5, partial sum integral. So let's do the usual. Step number 1, calculate the partial sum. We have done it on the previous board. Let's go quick. We recognize the series or sequence of partial sum being the powers of 2 minus 1, starting from 2, which is for the index n equal 1. Step 2a, so express a partial sum s of n as a closed form expression. S of n, the sigma from n equal 1, lowercase n equal 1 to uppercase n of 2 to the n minus 1. Let's open the toolbox quickly. We've done it just now. The sigma of the first, the sum of the uppercase n first term of that geometric series is equal to 2 to the n minus 1. Let's take that value, let's plug it in. N being a natural number from any value from n equal 1 upwards. Step 2b, express the continuous partial sum s of x. Sn 2 to the n minus 1. Let's replace that discrete variable with a continuous variable, x being a real variable. Step 3, let's calculate that partial sum integral. Calculate the PSI, which is by definition the integral from negative 1 to 0 of s of x dx. So that's the integral from negative 1 to 0 of 2 to the x minus 1 dx. Relatively easy. Let's open the toolbox. The integral of a to the x is equal to a to the x, exponential doesn't change, but divided by log of a plus of constant of integration. Here we have bound of integration, boundaries from -1 to 0. The bound of integration, therefore we can eliminate the constant or disregard it, and we just write as 2 to the x over log of 2, and of course the antiderivative of 1 is equal to x, so minus x. From 0 to -1, that gives us 1 over log of 2 minus 1 over 2 log of 2 plus 1. So when we expand all of that, we are left with -1 plus 2 plus 1 over 2 log of 2. So here, -1, of course, is a rational number. I'm assuming here that we know that log of 2 is not a rational number. Therefore, 1 over log of 2 is not rational, and 1/2 of it is still not rational. So we can decompose that number on a rational part as an irrational part. And finally, we can write that the sum from n equals 0 of 2 to the n, which is equal by translating the index, you go 1 down inside the sigma will be 1 up on the summation here. So sigma from n equals 0 to 2 to the n is the same thing as a sigma from n equals 1 to infinity of 2 to the n minus 1, which is what we are after, the monotonic divergent series of powers of 2, is equal to the psi after projection on Q. Therefore, we eliminate all that component irrational, and it's equal to -1. Happy? That's what we're after. So that value, or that graphical representation of that value -1 is here. It's that square. A unit square from -1 to 0, because that's the bound of integration for the psi. And below the horizontal axis, in red means negative value. So it's a unit square here. That's the surface of that unit square is equal to the value of that divergent series, a monotonic divergent series of powers of 2, after we have eliminated the irrational component. All right. Proof number 6, Ramanujan summation. So let us apply Ramanujan summation method. As a reminder, it's the sum from n equal 1 to infinity of a function f of n is equal to -1/2 of the value of that function evaluated at 0 minus the sum from m equal 1 to infinity of the even Bernoulli number divided by 2m factorials times the 2m minus 1 or minus first derivative of f evaluated at 0. Again, where b sub 2m is a 2m's Bernoulli number in the context of b1 equal plus 1/2. So if we use that formula with f of n equal 2 to the n, what do we get? F of n 2 to the n evaluated for n equals 0 give us 1, 2 to the 0 power equal to 1. First derivative 2 to the n times log of 2, evaluated at 0 give us f prime of 0 equal log of 2. Second derivative 2 to the n log of 2 squared, same, it will add another, multiply by another log of 2, which evaluated at 0, f second or double prime at 0 is log of 2 squared. f2m minus 1, first derivative of n 2 to the n log of 2 power 2m minus 1, evaluated at 0, give us log of 2 to the 2m minus 1. Relatively straightforward, and that formula will be valid for any value of m greater or equal to 1. You can see it here. So now, let's get some space. Leveraging from the hyperbolic cotangent function, COTH, cotangent hyperbolic, of x, by evaluating it at x equal 1/2 of log of 2, what do we get? We get hyperbolic cotangent of log of 2 over 2 is equal to 2 over log of 2, sum from m equals 0, we start at 0, to infinity of b2m over 2m factorial, log of 2 to the 2m power. Let's open the toolbox. What do we get? The cotangent, hyperbolic cotangent of log of 2 over 2 is equal to 3. So that's simple, we use it here. Again, b sub 2m is a 2m's Bernoulli number in the context of b1 equal 1/2. So let's rewrite that. We have the sum from m equals 0 to infinity of b2m over 2m factorial log of 2 to the natural log of 2 to the 2m is equal to 3/2 of log of 2. So we pass the 2 on that side and the denominator and the log of 2 at the numerator we have here. Or equivalently, we have that formula as well. So here we made two changes. First, we extracted the first number. For m equals 0, b0, it's 1. 2 times 0, 0 factorial, also equal to 1, so that's 1. And then for m equals 0, we have extracted the value for m equals 0 is equal to 1. So we are therefore equal to 3/2 log of 2 minus 1. And then we divide by another log of 2. You can see it was 2 to the power was 2m, it's 2m minus 1. So 3/2 of log of 2 minus 1 divided by log of 2 gives us 3/2 minus 1 over log of 2. Why do we do that? We'll see just now. Therefore, the sum from n equal 1 to infinity of f of n, negative 1/2 of f evaluated at 0, minus that expression that we found just now as per Ramanujan's formula. So minus 3/2 minus 1 over log of 2. So that value f of 0 is equal to 1. So f of 0 divided by 2 equal, of course, 1/2. Negative 1/2 minus 3/2 will give us a minus 2. Minus 1 over log of 2 give us plus 1 over log of 2. So then we can easily obtain by dividing by 2 the scalar number 2. The sum from n equals 0 to infinity of f of n is equal, of course, the n equals 0 to infinity of 2 to the n, which is 1/2 of the sum from n equal 1 to infinity to 2 to the n, which is exactly 1/2 of n 1 to infinity of f of n that we just had that expression. So 1/2 of this expression. So the negative 2 becomes negative 1 and 1 over log of 2 becomes 1 over 2 log of 2. That is the rational part. That is the irrational part. Remember, we need to project on a rational part. We know it will be a rational number, and that therefore it is equal to negative 1. So the Ramanujan summation works fine here. Done. Last proof, Abel-Plana summation. So let us apply Abel-Plana's summation method for monotonic divergent series. So the sum from n equal 1 to infinity of f of n is equal to, like Ramanujan, negative 1/2 of f evaluated at 0 plus I, the square root of negative 1, the integral from 0 to plus infinity of the function evaluated at it minus the same function evaluated at negative it over e to the 2 pi t minus 1. Remember, because we use the formula for the monotonic divergent series, we have this denominator. If it was for the alternate divergent series, we will have 2 times hyperbolic sine of 2 pi t. All right. Using f of s equal 2 to the s as a naming convention, it's a complex number. So f evaluated at 0, you can see it, it's equal to 1, easy. F evaluated at it, 2 to the it. F evaluated to negative it, 2 to the negative it. So we obtain the sum from n equal 1 to infinity of f of n is equal to the sum from n equal 1 to infinity of 2 to the n power. The value of f at 0, which is 1, negative 1/2, we have it here, plus I of the integral from 0 to plus infinity, 2 to the it minus 2 to the negative it over the same fixed denominator, e to the 2 pi t minus 1 dt. All right. Let's open the toolbox. What do we need here? We need that formula. The sinus of t log of a is a to the it minus a to the negative it over 2i. So if we compare here, we can see that we actually have that formula. It's 2i times sinus of t log of 2. So the 2i comes in front and then becomes 2i squared, and I squared, of course, by definition, it's negative 1. So the plus I in front of the integral becomes negative 2. So we are left with negative 1/2 minus 2 from the integral from 0 to plus infinity of the sinus of t log of 2 over e to the 2 pi t minus 1 dt. So that value is 3/4 minus 1 over 2 log of 2. That becomes negative 1/2 minus 2 of 3/4 minus 1 over 2 log of 2, which is by simplification, we can see here, negative 1/2, that one will give us negative 3/2, so it gives us a negative 2. Minus minus become plus, the 2 will simplify, we're left with 1 over log of 2. Therefore, the sum from n equals 0 to 2 of 2 to the n is also equal to 1/2 of the sum from n equal 1 to infinity of 2 to the n, which is therefore 1/2 of this formula. So the -2 becomes -1, and then 1 over log of 2 will become 1 over 2 log of 2. As that's a rational part, that is the irrational part. As usual, we project and we are left with -1. That's good. So let's draw the next board just to expand a little bit on that one and find out how did we get there, how did we figure out that formula. Okay, we have more space here. We leverage the expression of the inverse of the natural logarithm. Here it is. 1 over natural log of x is 2 over the harmonic mean of 2n x minus 1 minus 2 of the integral from 0 to plus infinity of the sine of t log of x over 2 to the 2 pi t minus 1 dt. So in that case, because of what we have here and what we have there, x must be different of 0 and different of 1. So like I said, the h of 2 comma x minus 1 is the harmonic mean of x minus 1 and 2, or 2n x minus 1. So let's open a toolbox. What do we get? The harmonic mean of 2 and x minus 1 is 4 times x minus 1 over x plus 1. But we are more interested by the inverse, which is 2 over the harmonic mean of 2 and x minus 1. It's equal to the inverse of those two values. 1/2 plus 1 over x minus 1. Really the inverse of those two. Multiply that sum multiplied by 1/2 is equal to the inverse of the harmonic mean. So let's use that. We just write the same thing again, and that expression using the toolbox gives us that value, minus 2 of the integral dt. Again, x is different 0, different of 1. So we use that formula now for x equal 2. What do we get? So for x equal 2, the integral becomes, of course, integral from 0 to plus infinity sine of t log of 2 over e to the 2 pi t minus 1 dt. That's this expression. X equal 2, we will have 1/2 here, minus 1 over 2 minus 1, which is minus 1, which is 3/2, and 1 over log of 2. So we can invert that harmonic expression on that side, which is again multiplied by 1/2, will give us 3/4 over 1 minus 1 over 2 log of 2. So again, 3/2 minus 1 over log of 2 multiplied by 1/2. Okay. And that's it. So we have seen and we have learned now that the sum of the monotonic divergent series of powers of 2 started from 1, so 1 plus 2 plus 4 plus 8, etc., is equal to -1. We have gone through 7 proof, and we have learned as well that this divergent series, monotonic divergent series, is stable. In other words, you can add as many leading zeros as you wish. It will keep that value of -1. You can also space that divergent series by equitably space all the terms by as many zeros as you want, as long as it's equitably spaced, the same number of zeros between those terms, it will still retain its value of -1. All right, so thank you for watching.